Welcome back, folks. The Bernoulli random variable. Okay, we're continuing on with this. The Bernoulli random variable can serve as a model. It needs to be a two-outcome situation. In this particular video, because there'll be another one, we're going to look at identifying situations suitable for modeling by Bernoulli random variables. A bit like in the previous video, we started work there. It's important that we break and just try and remember our terminology and focus on some notations, some of which will be familiar from an earlier study of discrete probability distributions, and a couple of simple tasks. Now the maths in this video is nice and simple. To kick it off now, we're going to look at 4 simple examples and we're going to run through these. So determine whether each of the following situations can be considered Bernoulli distributions. Can they be modeled with the Bernoulli random variable? So the first one is rolling a 6-sided, we assume fair die, and recording a success when a 3 occurs. Alright, well, we can see easily that that's broken down into success or failure. And remember, on the previous video we looked at the conditions for Bernoulli distributions. Okay, so go back to the previous video and we've got rolling this once, so it is a 1 at a time. So one trial, we're examining it after one trial, that's Bernoulli as well. And we can say that P equals, let's see, what's 6-sided, we're after one particular outcome, so that's 1/6. Alright, and fail, which by the way has the notation Q. Alright, so this is something a little bit new that I don't remember I put in the last video. So it's that complement I was talking about in the previous video. So that would be 1 minus a 6th. And that would be 5/6. Okay. So far so good. And 1/6 plus 5/6 equals 1. So there's another one of those conditions satisfied. So yep, all that checks out, and because there's only two possible outcomes, that is a Bernoulli distribution. So that one's a good one. Rolling a 6-sided die and recording the number that occurs. Okay, that's a little different. That one's not a Bernoulli distribution because we haven't defined what's P. And if we haven't defined what's P, then there'll be 6 outcomes, which is not consistent with Bernoulli distribution. So that one is not. Number C, part C, drawing a card from a deck 6 times with replacement and then recording the number of hearts drawn. Well, number of hearts drawn, what outcomes are possible there? Well, we could have 0 hearts through to 6. Yeah, so if we're doing it 6 times, it could be because it's replacement. So we could have 6, it's not likely. We could have 6, we could have 0, we could have in between. So that's not a success or fail. That one does not just have 2 outcomes. That is not a Bernoulli trial. Okay, we are drawing a marble from a bag containing 6 red and 4 green marbles. Doesn't sound so good so far. With replacement and recording the color of the marble drawn. This one could be modeled with a Bernoulli provided we define what a success is. Okay, what is our success? As long as it's defined, that's fine, and therefore we would have it could be, but it isn't actually defined, so I guess I should be stricter on it. That isn't, and it also says without replacement. So with some more work that could be a Bernoulli, but it's at this stage there's not enough information. It's not defined enough for a Bernoulli. It could be if you said if we were after looking at getting a red, if a red is success. It doesn't say how many times it's been drawn either, so if it's once, maybe. Okay, so that one's iffy, not yet, but I'd say no. Alright, it could be, but not at this stage. Needs a few things. Now let's look at our notations, and we're using them to describe Bernoulli random variables and Bernoulli probability distributions. And some of this is familiar from the previous video. So remember, these things are all about the probability of a success, and the success has to be well defined. Only 2 possible outcomes. okay, and the sum of them is 1. That's stuff we've definitely covered. Now I introduced one just before. I thought I'd introduce it before I got here, and Q is the probability of a failure on a particular trial. Okay, it's the complement of a success, and there's only those two outcomes. Now this letter, all sorts of letters get used for this, but if we're looking at the number of successes, let's say R defines that. Okay, the number, remember this is countable, it's discrete, okay, so it's a countable quantity, so the number of successes, okay, and that's R for, in this case. You can use other letters. For a single Bernoulli trial can appear like this if we're after a probability distribution table. Hopefully you can recall what a probability distribution is, but we will do that later in this video just to be sure. But you can see that there can only be two things. In a single trial of Bernoulli type, we can have no success, or we can have one success. That's it. If we have one success, the probability is P. If it's a fail, the probability is the complement 1 take P. Okay, and that's the entire probability distribution. Let's look at an example, and remember I warned you the maths is very simple in this video. It's atypically simple. Alright, a new hand cream has been developed for the treatment of a skin condition, and in the lab trials this cream is found to be effective 72% of the cases, and that forms our probability. Hope's doctor has prescribed the cream for her. Let X be the effectiveness of the cream, and we want to construct the probability distribution. So it's one of these sort of tables. Okay, so we need 2 rows. And because it's Bernoulli, we need 3 columns. Now, because we're not sadistic, we're considering the probability little p of a success is the probability of success with the cream. Amazing. So the probability of having success with this cream so in one trial, which is Bernoulli, we have probability. Now remember, X is the variable, okay, which we'll talk a bit more about in a minute when we polish up on our notations, but X is the variable. Alright, so that value of little p we get from the question, 72%, which we write as a decimal. So that'll be 0.72 there, and this will be the complement of 0.72, which is 0.28. That's our tabular form of the probability distribution. It's not the only form, it can be graphed, which you might know from your previous work. That terminology, just to be sure, hopefully you've got, by the time you watch this video, hopefully you've got the terminology all sorted, but there's 3 terms here I want you to be sure that you understand and can recall. So the probability distribution. What is a probability distribution? Well, here's the definition. It's basically talks about, describes or depicts the expected outcomes of possible values for a given data generating process. Probability distributions come in many shapes with different characteristics, and at the moment we're doing Bernoulli. Okay, the Bernoulli distribution, and it has quite a small probability distribution if in tabular form, because there's only 2 possible outcomes, success and fail. Okay, other ones have much bigger tables, whether they're discrete or otherwise. Okay, so next one is discrete. Remember, discrete variables, discrete quantities in general. Discrete random variables, that's basically data which is countable. It's the number of things. Okay, so we're looking at the number of successes or the number of Okay, so, and this isn't just for Bernoulli, this is for all situations that are discrete. So it's the number of things, okay? So one success in one trial would be Bernoulli, or one failure in one trial would be Bernoulli. But in situations where there's many trials, okay, which we'll look at in a future topic, n can be many in the number of trials. And it's things you can count, such as the number of students or the number of lollies, things that are countable, basically. Is it countable or measurable? Because if it's measurable, and we're not going to focus on this for a little while, but we'll get into continuous probability distributions. It's for measurable quantities, perhaps things like kilograms or meters, various things that can assume any value within a given range, okay? And the histograms, if you don't put it in a table, you can put it in a histogram, and the histogram will have columns, and whereas this histogram will have basically a continuous area, the area under a curve, okay? And that'll be covered later on, and basically measurable things that can have not fixed discrete values, but any particular value, because you can always increase the number of decimal places, alright? Okay, so there's no gaps, it's continuous. So hopefully we're all ready to continue on.